Welcome back to this lecture on functions. In this second segment, we're going to study properties of functions that allow us to classify them into three groups. The first class of functions are called one-to-one or injective functions or injections. And to be in that group, it must be the case that for all elements a and b in the domain of the function, this conditional must be true. Meaning, if it happens that f of a equals f of b, then it must be the case that a equals b. So what does that mean? What that means is that if two distinct elements in a domain have the same image, then it must be the case that actually these elements are not distinct, they must be the same. In other words, no two elements in a domain can have the same image. That's what it means to be one-to-one. Make sure you let that definition sink in and that you think about it for a while before moving on. The second category of functions are called onto functions or surjective functions or surjections. To be in that category, a function must be such that for every element b in its codomain, there exists an element a in its domain such that f of a equals b. So what does that mean? That means every element in the codomain of the function must have a pre-image. Again, I'll let you think about that one for a little while, and then we can move on to the third class of functions. These are called bijective functions or bijections or one-to-one correspondences. So a function is bijective if and only if it is both one-to-one and onto, as we just defined those two properties. So obviously, that third property is a stronger property than the first two, since if you're in the third category, then you must have both of these properties. So in particular, a function could have none of these properties, or it could have the first one but not the second one, or the second one but not the first one, or it could be in the third category. These are all the possibilities. So now, let's look at some examples to make sure we understand the meaning of these definitions. Our examples are going to look like this. I'm going to show you two vertical lines of black dots. The vertical line on the left, where we present the domain of the function, the vertical line of dots on the right, where we present the codomain. And notice I'm not going to name the elements in the sets, and I'm not going to put circles around them either. Now, to define a function, all I need to do is to define the mappings from the domain to the codomain. And here is one example. So my question to you now is to figure out which kind of function this is. In what category does it fall? You got it? This is a surjective function, or it's a surjection, or it is onto. Remember, the definition of this class of functions says that every element in the codomain must have a pre-image. What that means graphically is that every element here on the right must have at least one arrow going into it. That's what it means graphically to be surjective. Now, let's move on to the second example of a function. Here it is. Now, please pause the video and figure out which kind of function this is. Okay, now that was a trick question. I hope you saw that. This is not even a function. Why? Remember, a function is a relation that to each element in the domain associates exactly one element in the codomain. Well, notice this element here, the second element of the domain, is associated two distinct elements. In other words, it has two arrows going out of it. That is not a function. So in that case, we don't even need to worry about which category it falls into, since it's not a function at all. So keep your eye open to be in one of these categories, you must first be a function. Now to the next example. Please check that this is a function. Okay, you agree? Now what kind of function is it? Well, if you look at the elements of the codomain, you notice that every element here has either 0 or 1 arrow into it. And that is the definition or the graphical representation of an injective function. In other words, there are no pairs of elements in the domain that have the same image. So it's an injective function. Is it surjective? The answer is no, because there's at least one element, namely this one in the codomain, that doesn't have a pre-image or doesn't have an arrow going into it. So this function is injective but not surjective, so it's not a bijection either. It's just injective. Okay, let's look at the next example. What do you say? Did I trick you again? I hope not. This is not a function, so you don't need to worry about which category it falls into. Now remember, this one was not a function because there was one element that had more than one image. This one is different. It's not a function because it has one element here that doesn't even have an image. Remember, every function must associate exactly one element in the codomain to each element in the domain. And this element does not have that property, so this is not a function. Next example. So is this a function? Yes, it is. There's exactly one arrow leaving out of each of the elements in the domain. Is this an injective function? No, it's not, because you have at least one element here in the codomain that has two pre-images. In other words, it has two arrows going into it. So it's not injective. Therefore, it's not bijective either. But it could be a surjection. So is it the case that this function is surjective? And the answer is no, because this element does not have at least one pre-image. That is, it has no arrow going into it. Therefore, this is a good old function. It has none of the properties listed here, but it is still a valid function. Okay, let's do one more example. Please pause the video and determine whether this is a function and what kind of function it is. Okay, this one is not a trick. This is definitely a function. I hope you agree. Is this function injective? The answer is yes. There are no elements in the codomain that have more than one pre-image. Is this function injective? The answer is yes again, because every element in the codomain has at least one pre-image. So since it's a function, since it's injective, meaning no element here has two arrows or more going into it, since it's surjective, meaning every element here has at least one arrow going into it, then by definition it's a bijection. And this concludes our list of examples. I hope this will help you master these important definitions and categories of functions. Now let's consider one more definition pertaining to functions. Let C and D be any two sets, and let's assume that F is a bijection from D to C. Then it must be the case that F has an inverse function from C to D. That inverse function is denoted with this superscript -1 and is defined as followed. If f of A equals B, then by definition f minus 1 of b is equal to a, and vice versa. That's an equivalence. So what does that mean? That means if the image of a by f is b, then the image of b by the inverse of f is a. In other words, let's look at this graphically. First of all, for the function to have an inverse, it must be a bijection. So let's look at this bijection here. If the image of a by f is b, then the image of b by the inverse of f is a. What that means is you simply need to reverse the direction of the arrows and you get the inverse function. In particular, if this is the domain D of the function and this is the codomain C of the function f in blue, the inverse function will go in the other direction. It will have this set as its domain, this set as its codomain, and the arrows will be unchanged except they will go in the other direction. Now in particular, you should realize that if a function is not a bijection, that it's not invertible. In other words, it doesn't have an inverse function. For example, let's look at this function here that is surjective but not injective, so it's not a bijection. If you reverse the arrows, you notice that this element here now has two images, namely this one and this one, and that's not a function. So this function is not invertible. It doesn't have an inverse. Similarly, look at this injective function, which is not a bijection. If you reverse the arrows, what you get is not a function because this element here does not have an image in this set. So again, to be invertible means to have an inverse, and to have an inverse, you must be a bijection, a bijective function. Now let me conclude this segment by observing that some functions go from the set of real numbers to the set of real numbers. And some of these functions have inverses. But please do not confuse the inverse of the function f, denoted by this minus 1 superscript here, with the function defined as 1 over f of x. These two functions are most likely not the same. So in other words, this is not 1 over f of x. This is just the notation for the inverse function of f.